This video is going to show two more examples of how we calculate the pH of a weak acid. So, how do we calculate the pH of cyanic acid? And then it provides us with a Ka. So, I see the fact that I have an acid. I ask myself, is it strong or is it weak? Because I have memorized my strong acids, I know that this is weak. I'm also given a Ka, so that is screaming at me that this is a weak acid. So I need to do an ice table. So the first thing I do is I write a balanced equation. And I'm going to write it plus water, but I don't have to do that. The weak acid will donate a proton to the water. So this will be the cyanide ion and hydronium. And then I'm going to create an ice table, draw my fence, and I'm Xing out water because water is a pure liquid and is not included. So the next thing I do is I'm going to include my molarity. Under my cyanic acid, I have neither of these ions to start before this has ionized. And then I'm going to write my expression. So Ka will be equal to the cyanide ion concentration times the hydronium ion concentration divided by the concentration of the weak acid. Water is not included because it's water is not included because it is a pure liquid. So I have my Ka. I don't know my equilibrium concentration, so I'm going to use X. Hydrogen cyanide will go down by X, the products will go up by X, and then I'm going to add and get 0.20 minus X, X, and X. All right, in order to solve for X, I'm going to substitute into my equilibrium expression. So I'm going to start with my Ka, which is 4.9 times 10 to the negative 10th. Notice that that's super little, very small. Each of these are X, so I have X squared divided by 0.020 minus X. My Ka is so small, if I multiply that by 100, I'm going to get 4.9 times 10 to the negative 8th, which is way, way smaller than that. So, because my Ka times 100 is less than or equal to the initial concentration, whoops, that should be HCN. Initial acid concentration, that tells me I can approximate. So that's what I'm going to do. So this X is essentially 0. So I have 4.9 times 10 to the negative 10th equals X squared divided by 0.020. So X squared will be equal to 4.9 times 10 to the negative 10th times 0.020. That gives us 9.8 times 10 to the negative 12th. I'm going to take the square root of that, and I will get, let's go up here. X equals 3.13 times 10 to the negative 6th molar, because it is a concentration. In terms of sig figs, I ought to have sig figs. So I ought to have 2 sig figs. So this would be 3.1 times 10 to the negative 6. Now, I'm asked for pH, so since this is my hydronium ion concentration, I can say that pH is equal to the negative log of that value, so negative log of 3.1 times 10 to the negative 6. It's okay if here you're doing the 3.13 or even the entire number that's still stored in your calculator. It's fine. So the pH is equal to, all right, 2 sig figs here. That means 2 numbers after the decimal. So 5.50, which makes sense for a weak acid. Okay, next example. Talking about niacin. Here's a picture of niacin. Had to do an organic molecule for Dr. Quick. So showing you the structure, just as kind of review, this right here is that carboxyl group. Remember that this is a carbon, so that's that C double bond O, OH. This hydrogen is our acidic hydrogen. It's the one that is lost. So what would be left over would be this structure with a negative sign. So we want pH, gives us a Ka, so the Ka is screaming at us that this is a weak acid, so that tells us that we need to write an equilibrium problem. So I'm going to do that. Here we've got niacin, so I don't really want to write this all out, but I'm going to do it anyway. So we've got, this should be nitrogen. Here's our double bond. Carbon, double bond oxygen. Oxygen with a negative, whoops, this should be hydrogen. Sorry. Okay, I'm adding that to water. So that is going to give us, this hydrogen will go over here. So we are left with this ion and the hydronium ion. So we are going to set up our ice chart. That's a C, that's not an O. Okay, water is X'd out because it's a pure liquid. It is not included. We're going to start with this initial concentration. So that is 0.010 molar. Before niacin dissociates, we have 0 of either of these ions. I'm going to write my expression. So the Ka of, I wish I knew what this was called, but I don't know. I'm going to write niacin minus an H plus. It's probably really bad chemistry, but I'm writing it that way anyway. All right, so there is our expression, concentration of products over concentration of reactants. Water is not included because it is a weak acid. All right, because I have my Ka and I don't know my equilibrium concentrations, I know that these are going to go, the reactants will go down by X, products will go up by X because it's going toward the zeros. I get X and I get 0.010 minus X. Now I want to substitute into the expression. So I'm going to take 1.5 times 10 to the negative fifth equals X squared because it's X times X, divided by 0.010 minus X. This is small. If I take 1.5 times 10 to the negative fifth times 100, I get 1.5 times 10 to the negative third. So this is smaller than this, our initial concentration. So because Ka times 100 is less than or equal to the initial niacin concentration, I am going to approximate. So when I do that, I am going to get 1.5 times 10 to the negative fifth times 0.010. I get 1.5 times 10 to the negative seventh equals X squared. Oh, let me go back and talk about this. I have made this X 0, so it's kind of like it's not there. So now I want to do the square root of the 1.5 times 10 to the negative seventh. When I do that, I get 3.87 times 10 to the negative fourth. Whoops, not the X squared, that's just X. Sorry about that. This would be a concentration. So that is the concentration of this ion and the hydronium ion. So if I want to calculate pH, which is what it asked me, I am going to do pH equals negative log of x, which is 3.87 times 10 to the negative fourth. I know that I am using 3 significant figures here, and it should only be 2, so it should really be 3.9. Negative log of that answer, pH equals, if I have 2 significant figures, that means 2 digits after the decimal, so 3.41. Now, I left everything in my calculator, so if you solved, you may have gotten something slightly different. You don't need to worry about that for the AP exam. That's all taken into account. The next video will have percent dissociation on it, so watch that if you feel like you need it.